Welcome to this explainer on the Venturi effect, the counterintuitive physics shaping our world. This is one of those invisible rules of nature that literally governs almost everything around us. I'm talking from the tiniest, everyday objects you use all the way up to massive feats of modern engineering. And the crazy part? It completely defies our basic logic.
So to see just how counterintuitive this really is, let's try a quick thought experiment. I want you to imagine a fluid, say water or air, flowing steadily through a nice, wide pipe. But suddenly that pipe becomes much, much narrower. Does the fluid's pressure increase because it's being squeezed into a tighter space, or does it decrease because the fluid speeds up? Well, our brains immediately picture a highway traffic jam, right? Lanes merge, congestion builds up, and the pressure just goes way up. It feels entirely logical to assume water in a pinched pipe is going to do the exact same thing.
But here's the massive twist. The pressure actually drops. Yep, that's right. Higher fluid speed directly corresponds to lower pressure. When that pipe narrows, the pressure inside the fluid doesn't spike at all, it completely plummets. It is literally the exact opposite of that highway traffic jam analogy we just talked about. And that right there creates this perfect scientific mystery that we're going to solve right now.
Okay, let's dive into this. Meet Giovanni Battista Venturi. He was a brilliant 18th century Italian physicist, and actually the very first person to officially document this bizarre behavior. And get this, he didn't have any of the modern computer simulations or high-tech sensors we have today. Nope, he just had basic glass tubes, a powdered wig, and a relentless curiosity about how the physical world worked. Way back in 1797, Venturi made his really groundbreaking discovery. He realized that when a fluid passes through a narrowed section of a pipe, its speed rapidly increases while its pressure simultaneously decreases. Now, Venturi figured out what was happening, sure, but it was actually another legendary scientist, Daniel Bernoulli, who later used the principle of energy conservation in fluids to explain exactly why it happens. Today, this whole phenomenon bears Venturi's name, and it has honestly become an absolute cornerstone of modern engineering. Let's break down the mechanics step by step so we can really visualize the invisible here. First, water enters a wide section of a pipe. Here, it has low velocity and high pressure. Next, the pipe narrows into a bottleneck, which forces that fluid to speed up. And finally, as that velocity increases through the narrow throat, the pressure decreases. To truly grasp why this happens, we just need to look at two elegantly simple rules of physics. The first rule is called the continuity equation. It's simply A1 V1 equals A2 V2. Now A is the cross-sectional area and V is the velocity. Because liquids are largely incompressible, mass is conserved. Basically, if a gallon of water enters the wide end every single second, well, a gallon absolutely must exit the narrow end every single second. It can't just disappear. So to maintain that constant flow rate through a much smaller area, the fluid really has no choice but to accelerate. That bottleneck literally forces it to speed up. And here's where Bernoulli's equation comes into play. Bernoulli realized that a flowing fluid has a constant budget of energy. In a horizontal pipe, that energy is split primarily between pressure and kinetic energy, which is just its speed. So if you drastically increase the kinetic energy by speeding the fluid up, you have to balance the budget somewhere else. That energy has to come from the pressure. Higher velocity mathematically guarantees lower pressure. And this brilliantly illustrates the math in reality. Notice the manometers. Those are those vertical U-shaped tubes measuring the pressure along the Venturi tube. Over in the wide sections, the high pressure pushes the water strongly down into the tubes. But if you look right at the middle, the narrowest point we call the throat, the fluid is racing through at top speed, causing the pressure to absolutely plummet. The liquid level is physically lower, basically pulled upward toward the flow. It's undeniable visual proof that pressure drops right where the pipe is tightest.
From equations to reality, this is the invisible force powering everyday technology. So we've solved the mystery of the math. But science and technology are all about taking theoretical equations and turning them into real-world power. This pressure drop isn't just some quirky physics trivia fact. It essentially acts like a superpower. Because the pressure drops so low in that narrow section, it creates a vacuum effect that can physically draw another fluid right into the flow. And engineers have totally weaponized this quirk of physics to design our modern world.
Just think about some of the applications. Aircraft wings, medical nebulizers, carburetors, fuel injectors, Venturi flow meters, agricultural sprayers, and even perfume atomizers. When you squeeze a perfume atomizer, air rushes through a narrow tube, dropping the pressure and pulling the liquid up into this fine mist. It's just amazing that the exact same principle powering your morning fragrance is at work in heavy-duty agricultural sprayers, life-saving medical nebulizers, and even the carburetors of classic cars. They all rely on the Venturi effect to suck fluids into an airstream.
Now what's really interesting about this slide
is how this same effect even gives us the miracle of flight. Check out the cross-section of this aircraft wing. The top is curved, so it acts just like the narrow part of our pipe. It forces the air flowing over the top to travel much faster than the air underneath. And, as we now know, velocity increases, pressure drops. So you get low pressure above the wing and high pressure below, which literally pushes up against the bottom of the wing. That's enough force to lift a multi-ton commercial jet effortlessly into the sky.
And the principle scales flawlessly into massive industrial engineering too. This is the heavy-duty industrial Venturi flow meter in action on a massive pipeline. Instead of using really complicated internal spinning wheels to measure the flow of chemicals or oil, engineers simply narrow the pipe slightly. By measuring the exact drop in pressure at the throat, they can use Bernoulli's equation to calculate the precise speed of the fluid. From a delicate little perfume bottle to a mega pipeline, the physics honestly never change. So, what other invisible physical forces are shaping the world around you right now? We started with a completely counterintuitive question about a narrow pipe, and we ended up lifting commercial jets and measuring oil pipelines. The Venturi effect really proves that our everyday intuition is often wrong, and that the physical laws governing our universe are much stranger and honestly way more elegant than they first appear. So, the next time you see a passing airplane or even just spray a bottle of cleaner, ask yourself, what other invisible forces are you trusting your life to every single day without even realizing it? Keep questioning, keep learning, and thanks so much for joining me on this explainer.